we're ready, right? Okay. All right then. Then we're discussing, this paper, which is titled Implementation Strategies for Mutable Value Semantics. So, it covers a lot of ground. Well, already in the title there is implementation, there is semantics, and there is mutable values. And that's curious what that means and how one connected to the other. And the major part and major contribution of the paper, it exactly explains and formally specifies what mutable values are and what is mutable value semantics. And yet, there are 30 pages in the paper, so indeed it covers a lot of ground, in particular approaches to implementing the proposed semantics and even benchmarks of a prototype implementation, and for sure, some background, some motivation, stuff like that. And thus, basically what I want to talk about today is everything else in this paper except for this main part, that's formalization. For the simple reason that this formal part, kind of central part of the paper, looks like this. So they call it technical, right? This part is indeed very technical, which means if you're familiar with the notation, with this approach, models, these formalizations for languages, type systems, and stuff like that, then you can read it, you can understand it, build your mental model, and someone talking alongside doesn't really help, mostly distract. So makes little sense. If you're not familiar, again, this looks like gibberish, it makes no sense, and I won't make it any better for you. Thus, I see little sense in discussing this particular this particular part of the paper, and I think it's more interesting to discuss other parts. What leads to this formalization, and what we can take out of it on the other end, what conclusions, what benefits can we observe or at least expect. Moreover, the major idea for this talk is to use this paper as a sort of a springboard to discuss more kind of broader context of these contemporary newer programming languages and some developments in the older programming languages, and how it what motivates it. Because that's kind of huge part or major motivation for the mutable value semantics, thinking about it and formalizing it. These formulae, they serve a purpose. It's not for the sheer fun of formalizing stuff and writing papers. It has some motivation. So what kind of brought the authors to this stuff? Well, in general, at least in the programming language theory and academic community, bulk of the work, bulk of the issues and solutions revolve around the notion of local reasoning. And this local reasoning, also known as compositionality, really great thing, because attention span for people is pretty limited. We can't keep infinite amount of context in our brains, at least in the working memory. And surprisingly, for compilers, that's a challenge too. They cannot work with infinite context. Their capabilities are fairly limited. Besides, more often than not, we want and we need modular compilation, or what the proper term? Is it modular?
Yeah, I think modular is fun. Yeah,
There is particular technical term. It's раздельная компиляция по-русски. Separate compilation, right? Yeah, separate compilation. And yeah, even more than that, we often want separate delivery, kind of installing libraries ahead of time or after the fact, and linking the stuff together.
Could you elaborate on the point of the compiler having finite context? I thought that there is kind of an opposite direction in the literature, of super compiling everything together. Like if you have if you build a specialized server image, which can only pull the relevant parts of the operating system stack and of the library stack and optimize them for a particular purpose, and for that you need a superpowered compiler which has a lot of resources at hand. And I understand that what we're talking about right now is kind of a different direction.
No, not really. Again, there are kind of several things at play all at once. The technical term for kind of compiling everything at once is whole program optimization. There are optimizations, a host of optimization that require you analyzing the whole program at once, meaning actually not only code you wrote yourself, also all the libraries, the source code, or some kind of equivalent representation like AST already for all the stuff you use. So then we can analyze everything at once, kind of figure some stuff and optimize certain things that require knowing what other parts are involved. Every call site, stuff like that. And that requires a lot of memory, at least. So obviously whole program optimizations are not modular. You cannot whole program optimize part of a program, kind of separately libraries, separately stuff. It requires a lot of memory, a lot of resources for that, and usually a lot of compute time. Thus, there are very few compilers that perform whole program compilation, and usually they're unable to compile huge programs. Again, huge programs nowadays are millions to tens of millions of lines of code. And when you're compiling that many lines of code, that much, it becomes a challenge to fit it into memory and work on it all at once. Besides, that prevents you from delivering your program in parts. Separately libraries, separately your kind of binary or something that links to the libraries dynamically. So you only can statically link, then you have hard time updating your libraries, or harder time with dynamically linked libraries. You can swap a newer version of library. So there are many things at play. In some areas, in some instances, whole program optimization is a great thing and it works wonders. But more often than not, in kind of this enterprise programming world, we can afford that. We just can't afford that. That's too much resources, takes too long, too slow iterations. Then less flexibility at the runtime, at the delivery, stuff like that. And thus, really, we very often we strive for this modular separate compilation, modular analysis. It reduces the memory requirements and improves the speed of the compilation a lot. Kind of compilation speed for big projects is a huge thing.
Would you say it's mostly about build times or about developer times? I mean production build times versus development build times?
Well, it can be both. Again, that depends on your kind of whole setup. Yeah. If you're doing like continuous delivery, then basically your kind of development, debug build times are on par with your kind of production build times. You can afford overnight build for production, then like you don't have continuous delivery. For continuous delivery, you have to have pretty fast build cycle even for your production builds.
I guess what I mean is that it feels as though like the key metric here is like something like time to tests. So like development iteration time. I mean, production time is important, but we would like to have development iteration time like on the order of seconds. Production iteration time like on the order of hours is about 5.
Again, that depends on the project and the kind of life cycle. Another part, this whole program optimization for whole program analysis obviously contradicts incremental compilation. So if you're only doing whole program compilation and analysis, you can have these incremental parts.
Yeah, sure. Okay. If you do that naively, it absolutely kills like the idea of like seconds to tests in development. Yeah.
Then again, that kind of production build time depends on the scale of your project. If you have again millions of lines of code, and you have 5 projects, each 1 million lines of code, you have total 5 million lines of code. And if you need to deploy them all at once, you have to compile all that 5 million lines of code kind of simultaneously. And that might take you the whole night or whole 24 hours for the whole thing. All the analysis, compilation, optimization, everything. So you have 24-hour delay between your delivery to the production servers.
And then there's also a concern of like being able to deploy hotfixes quickly.
So again, for some cases that's not an issue. Many companies do not have millions of lines of code, and their iteration times does much faster, even if they do the whole program analysis. For others, that's just unacceptable. Just doesn't work. So anyway, this is a huge topic, very important topic anyway. For one reasons or another reasons, separate compilation, modular analysis, composable programming are really, really hot topics, and kind of that's major topic of the programming language research and development in academia throughout the whole history of the field. All right, so that's more on the technical side. About compilers, still they have limited capabilities, limited attention span, and people have even more limited attention span. So it's even more important for developers to reduce bug rate, to worry about some kind of global context, something you cannot see on your screen while you're writing your code.
And the so-called spooky action at a distance.
We'll come to that. That's kind of the main issue. And again, these issues arise both while we program and while automatic tools analyze our code. The authors somewhere here they refer to, or even they refer or here at all, and they were talking about code analysis. It's a system for finding bugs, statically analyzing code and finding actual bugs in there, which is deployed at Facebook at scale. They run their at least all of their mobile applications, source code for all their mobile application, they run through this system that does the static analysis. And that's apparently a lot of code, at least again, very often, many times a day. So they put a lot of emphasis on this modular analysis and developing again another formalism that analyzes source code separately, modularly and composably. All right, so huge win for again production deployments and finding real bugs, preventing real bugs from being deployed into mobile apps.
Which user references was that?
This one or here in Toll, that's about incorrectness logic, and they have a host of papers and a series of papers about incorrectness logic and systems built around that are deployed at Facebook.
Great.
Yeah, really interesting stuff. Highly recommend. All right, so another thing. Well, that's the major thing, and there are a host of kind of techniques that work with that. Again, kind of programming languages, theory, and academic community, a lot of attention and effort spent on developing type systems and type system like formalisms to analyze source code to prevent bugs. Again, the compositionality in that sense, modular analysis, basically a requirement for majority of the type system that studied in academia. That's maybe that's not necessary, depends on your definition. And basically there are type systems that are not composable, not modular, but there's very strong tradition, very long tradition for exactly composable type systems, and many people do not consider type system anything that's not composable. That's their definition.
Can you give an intuition for a non-composable type system?
Basic building block in our programs is a function. So any typing rules that span cross functions that consider some other functions. And not only signatures of other functions, that's obvious thing, that's inevitable, and that's composable. Okay, as long as we're looking only at a signature of another function, that's okay. That's exactly our composition. If we have to look deeper at the implementation of other function or some other information, semantic information apart from the signature, that's not composable. If we have to look through implementations,
a well-defined interface, if you think about it in terms of separate compilation, device and interface and implementation and
another thing is very understandable, I guess, thing is when we have this overloading, through inheritance and object-oriented programming languages, say, and if our typing rules are such that we have to find all the overloads, all the derived classes to check the correctness of the code, then it's not modular. In modular systems, we only look at the base class, the interfaces, that's it. We are not concerned about all the possible implementations, which again might be open set. Again, very well-known, famous and widely used totally uncomposable type system is C++ type system, right? Because of templates, we have to get these implementations of templates, instantiate them, stick them into the code, then we can analyze the types. That's not modular. That's why we can't have modular compilation for C++ templates. That's we have to put all the implementation of templates into header files and include them everywhere. And that's well-known limitation, and again, major thing that bumps up the compilation times for C++. Pretty famous example. All right, so yeah, stuff like that works like templates. Generally, yeah, impede modularity and compilation speed.
Mm-hmm.
All right, so nowadays the most well-known type system that enforces modularity in the presence of references and stuff like that is Rust. Rust is pretty famous for this ownership system. That's basically part of type system of Rust, and it's famous for its ownership system being complicated. In reality, it's not the most complicated ownership system. I've seen worse, much earlier than Rust. On the other hand, again, these rules, ownership rules, are mostly the stuff that C++ developers were following anyway. That's kind of the rules. There it's rule of thumb, so to say, that prevents you from making mistakes, from leaking resources or accessing already freed memory and stuff like that. Yeah. There you just have to check that yourself as far as you can, and Rust make it formal, and compiler checks that. And again, because compiler have limited span, yeah, these ownership rules are kind of over approximation. They are sort of overly restrictive to make things simpler, actually. That's again.
Simpler for the compiler.
Yeah, for compiler, for analysis, again, doesn't matter who does the analysis. For programmer that analyzes the code, it's again simpler because it's more modular, less context needed, and that's why it's again a bit simpler system than some previous attempts, which were much more complicated, in particular because they weren't that modular. Anyway. Because these rules still pretty kind of hairy, pretty sophisticated, Rust kind of spun a number of newer languages as a reaction to Rust that try to achieve the same level of safety or comparable level of safety with much simpler rules. And again, there are two approaches. Another very famous example is Zig language, which gives up some of the safety guarantees, static safety guarantees, but simplifies the type system significantly, and still retains other safety guarantees, kind of compared to C++ languages at least. Another kind of line of research, partly reaction to Rust, partly started before Rust. Again, there were certain reasons why they developed Rust. So for same reasons, other developers developed other languages, and they moved into this, what we now know and understand as mutable value semantics. And at least mutable value semantics is one approach to this notion of second class references. Kind of that language developers realized that, okay, most of the complications in the Rust type system ownership system stem from these first class references. Meaning, okay, we can obtain reference to a value, basically any value anywhere in Rust, yeah, in heap, on a stack, whatever. We can obtain a reference and we can pass this reference around, stick this reference into a structure, and then, yeah, we kind of encounter all this host of problems, especially in C++. Yeah, when this reference might become invalid while our program executes. We have these dangling references, dangling pointers, references to freed memory or kind of reallocated memory, kind of all sorts of pointers that now point to their own location, not what they were meant to point to. Yeah. So Rust enforces a lot of these rules to prevent these errors, prevent pointers or references from becoming invalid. Okay, another obvious kind of solution, no references, no problem. If we don't have references that we can kind of pass around, stick into structures, they cannot become invalid anyway. So that's the meaning of second class references. Well, if we have no references at all, that's like no references. Okay. Neither first nor second nor third class. No class references. Second class references means that we still have references in certain places, and we will see exactly the places or the only place where we get references, but we cannot kind of pass them around freely, and above all, we can stick them into our structures as fields. So they cannot kind of escape certain boundaries. Again, modularity. Basically, references don't escape structures or functions. Sorry, references don't escape functions. That means they're second class, and safer. Now, yeah, how that works exactly, what that all means. If you don't have any further questions.
Yeah, I'm good.
All right. Let's start with values. Yeah, we have mutable value semantics. So, okay, what's the deal with values and what's value, what's not value? Major example of values in all languages are primitive types, like numeric types, integers, doubles. Yeah, they're kind of this thing that's kind of whole, and it's always kind of here the whole thing. I know. When you assign these values, primitive types, to variables, you copy the thing as a whole and you get new value. In C++, you can get a pointer or a reference to this primitive value. But that's kind of different thing. The value itself kind of stays the whole, and it's kind of atomic in this sense. And that's the base of all the languages like Java, C#, even JavaScript to a large extent. And that's kind of what we expect and understand from the values. Yeah, these are the prime example. You copy the thing, you get new thing. You assign it, you get new thing. You change one thing in one place, it has nothing to do with any other value, even if it was the same value. Like 2, okay. We have integer 42 here, we have integer 42 there, they're completely separate. We bump one, it becomes 43, the first one stays 42, no matter what. That's not the case with kind of reference types. Yeah, and in Java, all the compound types are classes and they're reference types. So they're allocated in heap That's details of the implementation, but okay, we all know they are located in the heap. And what we obtain is a reference to this thing, to this object in the heap. And when we pass these things around, we only pass references. And if we pass the same reference, the reference gets copied, but the object stays the same, and two references point to the same object. That's kind of the definition of this reference semantic. Here we have this illustration. Yeah, when we have kind of 2D point, and the context of this 2D point is these value types, and they are distinct. X is one thing, Y another thing. They never gets confused. Even if we assign the same value, that's still two different values that gets kind of changed separately. That's not the case if we use this vec2 class or objects. Here we have again two fields of this vec2 type. One supposed to denote position and another one supposed to denote dimensions of the rectangle. And again, they are supposed to be separate because position generally has nothing to do with dimensions. They are kind of orthogonal in this sense. But if we set both fields to the same reference or two references to the same object, now they are, mixed up. And changing position cannot be done without changing dimension because it points to the same physical object in the memory. Okay, that's kind of well-known, well-understandable behavior, kind of the definition of this reference semantics. But yeah, one thing, it's kind of pretty distinct from this simple value semantics. So we always have this value semantics, behavior of the values in our language, or value types, and behavior and semantics for reference types. That's why in particular C# improved on Java and explicitly introduced value types that compound types, like structures, but they behave like values. You cannot really obtain a reference to this value type, to a structure. Well, in unsafe sharp, you can obtain a pointer to that, but that's a different story. Still, kind of by default, they behave exactly like ordinary values. They get copied around when we pass them or assign to different variables. And they have nothing to do with one another. Changing one does not affect all the other values of the same type. Okay, so having two semantics in the same language, like in Java or C#, still we have some types that implement value semantics and some types that implement reference semantics, and you have to distinguish. You have to know which one you use because they will behave differently. And that's a bit confusing. Again, obvious kind of way out is to only have value semantics for everything, right? That kind of simplifies the language. Here is a picture that illustrates the same thing I just talked you through. Here, like the difference between values and pointers to the values. And when we have several pointers to the same object. And here is the picture when we have kind of the same logical structure, but only with value types. We always have copies of these value types and they form only a tree, proper trees. Yeah, this thing kind of, well, this is a way to draw a tree, basically. If we replace kind of these boxes with arrows, then we will see a tree, right? Anyway, trees define this kind of nesting structure. And here we draw the nesting with boxes. Here it's not a tree because yeah, we have
because arrows go like
yeah, we have arrows that point in the same thing. So it's more general form of a graph. Trees are very simple graphs, and yeah, object graphs in general in languages with reference types can form arbitrary graphs, directed graphs with cycles and everything. That's not very pleasant to work with, both for human programmers and for compilers and runtimes. Yeah, complex graphs are tricky to analyze and make sense of in many instances. So value semantics, mutable. Well, anyway, mutable or immutable value semantics simplify that and turn all our graphs into trees, which are really simple things, really easy to work with, to understand. Yeah, here like the same example re-implemented in Swift, which kinda has sort of mutable value semantics, at least like half of it. Basically in the same sense that C# has that. So in Swift we have these value types, like in C# we have value types. Yes, the structs that implement value semantics. So we can use that for everything, and they will get copied around, and we will have these nice trees instead of pointers pointing to the reference pointing to the same physical objects. It's just basically syntax how we write it down in Swift, and the important part here is this var declaration, designation, meaning again mutable. Swift has mutable values that denoted by var values, kind of variables or fields in structures, and immutable ones denoted by val, kind of again usual thing. Here we everywhere use mutable stuff. All our values are mutable. We can change them, but as long as they're values, they get copied. So changing one value doesn't affect another one in any way. That's the win. Again, that's like not an issue with immutable values. Kind of functional programming languages are huge on that. Yeah, immutable values form the basis for functional programming language, and as long as all your values immutable, aliasing is unobservable. Even if and that's kind of usual thing for functional languages, use pointers everywhere, referencing everywhere, not copying what you don't have to copy. And still we maintain value semantics. Well, as long as we cannot change value, okay, we cannot kind of change another one accidentally. No changes, no problems. Yeah, again, that's a huge win for functional languages. They have a lot of tricks up their sleeve when they kind of get a lot of mileage from using pointers and using these persistent structures that share a lot of common parts and kind of change, update, create new small parts, kind of very incremental, and conserve memory in that way, and kind of in other cases improve performance. But that's kind of different world. Here we are concerned with values that we can change in place, and that's again boils down or revolves around these compound values structures, because changing like single value as an integer, if we change the whole value, kind of replace old version with new version, that's not really mutating. We can easily model that in functional languages with immutable values. We just kind of introduce new binding that now binds to these new values. That works exactly like mutating variable, but replacing the whole thing. Again, this mutation is unobservable anywhere else in the program. it's only local. And indeed, many functional languages kind of implement some just syntactic sugar to make kind of impression we're mutating like in imperative languages, but under the hood we just rebound things, and that's still totally immutable and functional. No problem at all with that. It's not the same as in-place mutation. So we want to have in-place mutation for various reasons. Again, performance reasons in many cases. But we want to maintain value semantics. And this is what this paper is about, how to merge these two worlds. Have both kind of structure that we can mutate piecewise. Mutate piecewise and still maintain value semantics. So kind of keep this illusion that we copy everything, but at the same time, at runtime, not copy everything, because that's too slow, drops performance too much. We want to kind of do the smart thing and mutate only and copy only what we absolutely need, and use several tricks, a host of tricks that are partly described in this paper to improve performance and pretend only maintain this facade that everything is by value and copy it while it's efficiently kind of passed around under the hood in the runtime. Yeah, again, spooky action at a distance, the term that we already mentioned. Here the major thing is kind of funny thing, but on the other hand, totally not funny thing. Due to this referencing, kind of returning a reference to an array, Java had a security vulnerability in the applets security model. There was a thing called Java applets that ran in the browser. They're supposed to be isolated and secured. But at some point there was a issue having to deal with this array with signatures. The thing being, arrays are reference types in Java, so we pass reference to arrays around, but arrays themselves are mutable. We can change parts of this array, elements of this array. Here again, array declared as final, meaning we cannot swap new reference instead of old one. We can replace this array with another array, but we can work with that same array. And that was the issue. And malicious code could obtain a reference to this array and then change one of the signatures or identities in this array to its own identity and do kind of bad stuff, whatever they wanted to.
So is the current standard fix to that in Java to do defensive copies?
Yep, basically Not only in Java, in pretty much all the languages. And again, this is kind of this into your face example because it's security vulnerability. I think there are relatively few security vulnerabilities of this type, but I bet there are kind of a ton of just plain old bugs in the code due to passing references and then mutating the reference while kind of author thought you're not supposed to do that.
Yeah, absolutely.
Yeah, I bet developers in all sorts of projects encounter that pretty much on the daily basis. And then, pretty much the only fix you have is to copy and give out a copy to your thing, your structure.
I mean, you can always call your place a comment. Please don't mutate.
Yeah. something like that. Stuff, becomes interesting on the border between your code and library code. If you cannot kind of harass library maintainers to change their library and do some other thing, well, maybe, and you don't want to take up the burden of maintaining a fork of that library, right? Yeah, basically the only way out is to copy thing and pass there a copy, so it doesn't mangle your data. So I suspect there are a lot of bugs that lead to unintentional either corruption of data when something modifies the thing that it wasn't supposed to, or other way around, we do too much defensive copy and we pass copy and something modifies the copy and the changes do not propagate where it's supposed to. So we have this split brain kind of problems in the applications.
As a side question here, so I understand that this paper proposes the solution of like using value semantics for these kind of situations, but it also feels like we could have like a mechanism of having a reference and being able to, or let's say having a handle and being able to attenuate like the permissions it has. Like we have a read write handle and we can only pass a read handle or something like that.
Yep, totally. Well, that's part of the Rust type system. Yeah, it distinguishes between mutable values and immutable. Mutable references and immutable references. So, you separate that, and you know when you pass mutable reference, and thus, or API requires a mutable reference, and then you can figure out that it's going to mutate your value. Then you know, okay, if you don't want it to mutate your precious value, you copy it and pass a mutable reference to a copy, and then do whatever you want. And if it takes immutable reference, you know, okay, you can give up this reference and it won't change your value whatsoever. There are more involved type systems that distinguish more kind of shades of gray.
Yes, so it also, like, from my side, it kind of makes me reminisce about object capabilities.
Yep. Yeah.
So, like, has there been any connection of like a language with object capabilities built in at the level of type system or something?
Sure. Pony, the major example of a language that built around object capabilities essentially, and it kind of distinguish quite a host of these capabilities. Access rights from the owned objects to kind of mutable access to immutable access to epoch access when you have a reference but you don't even know what it refers to, and you cannot do anything with this reference apart from storing it and passing it further down the road. Probably there are other languages with this sort of object capabilities built in. Still, again, kind of Pony, rose to some prominence before Rust, and it was again famous for having this complicated type system, somewhat confusing type system around these object capabilities. Many people were confused, like why you need all these shades of gray, all these distinctions, and how to efficiently work with that.
Value semantics are of course easier than that, sure.
The aim of newer languages and value semantics is to simplify this stuff, kind of provide bare minimum capabilities that's safe, that easy to reason about, easy to work with, prevent major mistakes, and still kind of optimizable enough to provide decent or even very good performance.
Mm-hmm.
So this is what this section discusses. basically this object capabilities and separation of concerns, kind of the reference to thing, kind of ownership of a thing, or access rights to a thing, what you can do with the reference.
I'm impressed by the jumpy names like spooky action, murky depths.
Yeah. This section is about these deep copies versus shallow copies. When we have reference semantics, we have this question, okay, when we copy, do we perform deep copy or shallow copy? Shallow copy, again, distinction between deep copy and shallow copy doesn't exist, doesn't make any sense for value types because they're always copied like wholesale. You can't shallow copy them. But for reference types, okay, you can either copy just the reference itself, and that's shallow copy, or you can copy the object and obtain the reference to new object and put there new reference to new object that's separate from the old object. Then you have a question, okay, do you perform the same thing recursively for your object because it might have reference fields inside? So do you have like recursive deep copy, or do you do not do that? And here they provide an example where you can't even decide beforehand, like once for all. In this case, like, if you copy a button, makes total sense to perform deep copy of the position, but it makes no sense copying the handler. Like, what's the meaning of deep copy of a handler? Like, you have a separate instance of the handler that does exactly the same thing. Like, you're just multiplying the code out of nowhere. It makes no sense. So for in reference semantics, for this class or classes like that, you have this mixed copy. Like, some parts you copy with deep copy and some parts you copy with shallow copy.
Well,
that's kind of confusing.
I mean, I find this a little confusing because I'm not sure I see a qualitative difference between deep copy in position and handler. It seems like we should always do copy on write.
Again, copy on write, a kind of orthogonal thing. That's a bit of different semantics in itself. Again, here we use copy on write as an optimization strategy, implementation strategy. Even copy on write for handler, that's like more complexity out of nothing.
Oh, what I mean to say is that
click handler is essentially a function, and there is little point copying functions around, having several separate copies of a same function. It makes no sense whatsoever.
All right,
so we never copy that.
Yeah.
In particular, copy on write, okay, we'll never copy it because we never write to a function. We don't change the body of a function at runtime. And that's like, okay, more machinery, more these checks for the things we never modify whatsoever.
Yeah.
On the level of semantics.
We could modify them.
Yeah, that's really tricky on many levels and makes little sense. Really, really little sense. Self-modifying code is
I was
mostly useless.
More about interactive development in the style of Lisp or Spring, maybe.
And that's again the difference between modifying the value itself and swapping new value altogether instead of the old one.
Yeah, I think those are not only about modifying functions in place.
Nope.
No?
Nope. Now, modifying functions in place is, self-modifying code, which basically prohibited. Or, again, well, kinda JIT compilers kinda sort of do that. Kinda self-modifying code, but that's a very kind of deep technical story and very narrow use case. For the rest, well, actually, for much of the even JIT compilation, you just generate new function and swap the reference from old function to this new one and go from that.
I guess this is a question of implementation, but so like imagine, I can imagine, so like consider we are debugging something and we have a debugger which allows us to live change the running code as well. So like we stop and we can change what's going on afterwards. And I can imagine an implementation strategy which swaps references and and which modifies code in place. So
well, theoretically that's possible. In practice, kind of modifying the code of the function in place is so kind of technically challenging and hairy. It's not worth, just simply not worth it. Like, what you gain going this route? Basically nothing compared to just generating new function wholesale. So you get no advantage for a lot of headache. That's why nobody really does that.
Yeah, sure. If you grant that, then the discussion about mixed copies makes sense, right?
Yeah. Like that. Again, that kind of highlights this distinction between mutable values that we understand as compound values, and we are mutating parts of this value, in contrast to swapping the value wholesale, which is easily done in functional languages with immutable values. That's our two different stories, and we're focused on the first one, when we swap parts of the values, parts of the objects in place, and go from there. Now, this mutable value semantics kind of circumvents this question of whether you copy deep or shallow. Basically, you always perform deep copy, or something that looks like deep copy always. You maintain this semantics of copying values around, even if you use copy on write under the hood. That again, kind of connects to this UML and all distinction. In UML, you have lots of these arrows, right, for all kinds of uses. A distinction, composition from aggregation and from association. So, but in most of languages, all these relationships are kind of represented by reference. You have a reference to something else, and you don't really know whether it was supposed to be a part of the parent object or was it just associated. So we keep it to kind of have access to functions, methods of another object, and like we compose. The distinction between this composition, aggregation, association kind of lies basically precisely along this line of whether we do deep copy or shallow copy of this thing, whether we need to copy, whether we own this thing and we have to maintain ownership. And that's kind of whole part relationship. Kind of the whole thing, the compound thing, owns parts and takes these parts with it. So we copy parts, but we don't touch this stuff that we only reference, that we don't own, that we associate with. All right, there was that. Yeah, so mutable value semantics is focused on representing this whole part relationship or composition, and it not really concerned with representing other kind of relationships. Yeah, as long as we don't have these references or pointers, we can't natively represent this association thing when we kind of know about something there, but we don't own that, we only mention that, and we don't carry that around with us, we don't copy that, we only kind of access this thing. We can represent it directly, but we have, again, the same techniques that Rust has, say, using indexes in a structure to represent this association. In Rust, that's kind of employed very often. We have allocate kind of continuous arrays of stuff, and then instead of pointers, we use indexes in that array when we need this kind of handle thing or association, represent this association relation, but we don't want to mess with, immutable, mutable references in Rust, and having host of references logs stuff in place.
A little confused here. So I was saying that we use just integers as indices, or that we use array slices as indices, or do these exist at runtime?
Sure, this stuff exists at runtime. Index can be many things depending on a situation, or handle can be implemented in various ways. It can be just integer index in an array, kind of position in array or something. It can be your path in a tree, it can be other stuff.
I'm just asking about the implementation strategy in Rust. You mentioned how much compiler support do we get in this strategy?
In Rust, you have both things. You can have references in Rust, right?
Yeah.
Both mutable and immutable in general. So you can represent this association relation with references, like honest to God references. Plus you have boxes, you have reference counting stuff. You have a lot of mechanisms in Rust. Still, because other mechanisms, anything that uses references is prone to this. References become invalid during runtime. You have restrictions working with them. Thus, when these restrictions are kind of too prohibitive for your application, your use case in some cases, oftentimes Rust developers can resort to using indexes into structures, not using direct pointers, but replacing that with indexes.
You mean using literal integers?
Yeah. Or integers, or handlers that are some kind of interface around an integer.
Alright. So that's basically a compiler escape hash.
Kinda. Sorta. Yeah. In a way. Well, that's one way to look at it. There are other ways to look at it, right? That's kind of up to interpretation. Again, Rust has both things. One of the kind of intentions of Rust as a language is to have it all. Kind of have all the mechanisms. But with different mechanisms, you have different restrictions to preserve correctness of your code. Thus, you use whatever makes sense for particular use case.
Can I have a break?
Sorry?
Can we have a break?
Yeah, sure. You're the one responsible for the montage. All right. And then there is this question of semantic regularity and general programming. General programming, generic programming, semantic regularity and generic programming. Yeah, generic programming kind of assumes that you're write these generalized algorithms that do the same thing for like host of types, right? For different types, they do the same. It was popularized by Alexander Stepanov, if I remember correctly, Stepanov's name. For C++, yeah, then C++, kind of this notion, the idea of generic programming, yeah, got a lot of popularity in C++ community. Some people go as far as saying that, yeah, this is like true C++. It's generic programming, the rest is like old stuff and kind of incidental there. Anyway, in C#, in Java, pretty much any language, there are at least some mechanisms for generic programming in the form of generics, generic classes, generic methods that are parameterized by types. And yeah, they're supposed to provide the same logic, the same behavior, whichever type you pass as an argument, as a type argument. But if we have these two semantics in our language, like value semantics and reference semantics, that behave differently with respect to assignments and updates, that kind of means you cannot use these updates, mutation in your generic code, because it won't work the same for these different types of semantics. For value types and for reference types, it won't work the same. It will work differently. Indeed, that causes kind of some grief for Java developers and even C# developers. In Java developers, you basically cannot use these value types, use generic collections or methods, and yeah, you have to provide specializations for value types or for arrays of value types and stuff like that. There are a host of specializations in standard library. In C#, this stuff is more automated, but still, yeah, it provides one implementation that behaves one way for reference types, and then for value types it specializes, generates kind of different implementations at runtime for your value types that you use with generic collections. But still, yeah, a lot of stuff goes under the hood. It kind of, yeah, mixes stuff up. Thus, there are a lot of reasons why we might want to simplify our language and have only one semantic in the language. Like, okay, value semantics and only value semantics. Again, that's a big part of functional languages because they have value semantics everywhere because the values are immutable. It's really easy to implement this value semantics. Indeed, it prevents many kinds of bugs. It simplifies reasoning. It aids this generic programming. Many good things. In other cases, it has performance issues. That's why we want kind of best of both worlds. We want to maintain value semantics and still add their mutations in a sane way, kind of principled way that still prevents lots of errors, but provides performance benefits when we need them and where we need them. This kind of guides us into the next section, overview of this Swiftlet language. In reality, it's not really a programming language. It's kind of glorified calculus. Calculi of various types are bread and butter of programming language theory and programming language research. And in academia, we do research on programming languages by proposing, inventing, formalizing various calculi, one calculus or another for different purposes, and we studied their properties. Calculi are like programming languages, but kind of simplified to bare bones minimum. Like they're not really viable programming languages. They have too few features. Swiftlet is like that. It has like very, very, very minimal set of features. Basically, only the feature that necessary to kind of formalize, analyze, and validate this value semantics, and not really much stuff to actually program in this language. But still, it provides. Okay, let's kind of overview what it provides, what it really has. Kind of following this Swift example, or Rust example for that matter, whatever, Scala example. We have distinction between variables and immutable values. Variables are introduced with var bindings and they're mutable. We can either mutate the whole thing or fields of a structure, of a mutable fields of mutable structures, and we'll get to that. Immutable bindings or variables that introduced with let, we cannot mutate whatsoever. They just stay the same always. Then we have structs for compound values. Structs are defined by their fields, and fields might be mutable, again var or let fields that are immutable. Immutable fields obviously are assigned at the construction time of the structure and never change during the whole lifetime of the structure. What else do we have?
Will we be able to finish in half an hour?
No way. What we have, apart from this short section that introduces these features, okay, structure, then arrays, then functions. That's basically all there is to the language. Then we have like implementation techniques, then optimization techniques, and then benchmarks. 3 more major sections in the paper. And we're skipping this central part with just formalization as it is.
Oh, it would be good if we would do that.
Okay, realistically, we will need about an hour more to cover the implementation and optimization ground, even without much details. Anyway, let's kind of continue and see how far can we get. All right, arrays and functions in itself, kind of usual stuff. The interesting stuff starts when we consider in-out parameters of the functions, of our functions. So that's exactly the place where second class references enter the picture. In-out parameters are exactly our second class references. So semantically, in-out parameters are exactly references, but we can only work with them like with values, usual values. We can mutate them, mutations happen in place, but we cannot assign the reference itself. We can only assign, again, a copy of an object when we do assignments. Though we can replace, again, in place in the caller function, the value holds the whole value of this in-out parameter. The tricky thing about in-out parameters is the references. So generally, if a function have several in-out parameters, we could, in principle, pass references like two references to the same object as two in-out parameters, and then we would have aliasing on all the problems inside the function that that result from aliasing. And Swiftlet and its type system exactly prevents that. So again, we have certain rules that prohibit us from passing and possibly passing references to the same object, physical object in memory, through two different in-out parameters into the function. Well, major thing is, okay, you cannot pass the same object as two times. You cannot mention two times in the call of a function in as an in-out parameter. No, and then the same for arrays. You can pass two different elements to different distinct elements of a same array, but you cannot pass references to the same element of the same array. And yeah, we kind of over approximate that. If you have some calculated, we cannot say which exact element of array you pass, and you cannot have two elements of this array passed as an in-out values, because they might alias at runtime depending on the calculations. Yeah, depending on runtime calculations, so that's statically prohibited. That's where we over approximate, kind of usual thing. The major thing is, again, we cannot return in-out parameters, in-out references. We only ever return values. That's when we return something we got even as an in-out parameter, we would copy that. That's how we kind of maintain this value semantics in the presence of reference, second-class references in the form of in-out parameters. That's the major thing of the language. The rest is, yeah, basically usual stuff. Yeah, we can easily swap values in our the caller method through in-out parameters, or mutate the values themselves. But we always know when we pass parameters by reference as in-out parameters, we denote them with ampersand at the call side to visually distinguish passing by copy versus passing by reference. Yeah, this kind of illustrates the case when we swap. We use this function swap to swap values, like a value that's inside some structure with the value that's outside this structure. We can do that. So we can pass as in-out parameters kind of whole things or parts of our structures. That's not prohibited, as long as all the values are totally distinct and cannot alias the same value, the same physical value. Then, yeah, we use explicit captures for our closures, but that's, again, technicality, not very important. Yeah, to kind of model, again, this generic programming, here we use the any type. So in this language, in this calculus, they do not implement these generics, like types or methods parameterized by other types, but they provide these mechanisms of any types that can, how to say, you can assign any value of any type as a parameter or field of type any, obviously. So you have these mechanisms to implement genericity through that. Again, this is akin to how Java uses object and type erasure under the hood to implement these generics. And, well, lots of languages use type erasure. That's like main mechanisms. If you have properly implemented generics in your language, in your type system, if they are sound, then you can just erase the type information and use some general type like any or object or something, pass it everywhere, and that will not break any code. So the Swiftlet only provides these lower level mechanisms for implementation, but not generics themselves. But yeah, you can implement generics on top of that in a usual way. So we skip this formal presentation of this Swiftlet calculus. The major thing about this formalization, they provide two semantics of the language. Higher level semantics in the form of basically big step operational semantics, and then lower level small step operational semantics. The first one, the first semantics is employed to prove that, again, the typing rules, these rules that govern in-out parameters, really preserve mutable value semantics. So they don't break, they never produce aliases. That's statically guaranteed, that no way, as long as these rules are enforced by our compiler or type checker, in the semantics, we always get this value semantics. And we never alias the same value through several references. While the lower level operational semantics is employed to prove usual stuff like type preservation, soundness of the type system, that everything works as intended. We never hit these errors, exceptions, or stuff like that. Well, again, they're formalized, they explicitly state the properties they prove. When they prove them, that's kind of particular part of the safety guarantees. Okay. The rest is, the formalization and the proofs, which we will take at the face value. We will believe that, really this stuff works as intended and the proofs are correct and they really prove the properties. Soundness, for instance. These are definitions, around memory state, and so that our programs don't corrupt memory. Say that's one part of the guarantees and type soundness that that they prove. Okay, so after we got the proofs, we can talk about implementing the semantics. We have formal semantics. We can implement it, or we have to implement it in the actual compiler. And then on top of that, we can employ certain optimizations that preserve the semantics but improve the speed of our programs. This is usual architecture of the compiler, and they use LLVM framework to generate actual code, and that also opens this possibility to later benchmark and compare to other languages and compilers that use LLVM framework. In particular, they compare with C++ via Clang, compiler Swift via kind of usual Swift compiler that again built on top of LLVM, and Scala native, which also uses LLVM to produce native code, native binaries for Scala language. Right, now, how actually we implement the stuff at a lower level. Suppose we know what is LLVM and how it works, what's SSA, single static assignment, and all that stuff. Okay, we have to somehow represent the values, yeah, our language works with. Again, that's like usual numeric types, that's structures, that compound types, that's arrays, another compound type, that functions and closures in particular. Yeah, and that's all values we have in our language. Then also we have to deal with in-out parameters. And that's what we consider. Also any type. We have some representation for any type. That's we consider now, and yeah. Again, all of them have built-in support, pretty sophisticated support for numeric types, both integer and floating point types, and structures with various annotations, kind of padding and not, like, yeah, it's pretty sophisticated, well-developed support. So the authors use built-in LLVM capabilities to directly implement value types and structures. Nothing interesting there, but arrays are more interesting. Yeah, again, arrays are big chunks of memory, especially when we have this value semantics. It means that we store values inside arrays, not references to something, but values themselves. That makes arrays even bigger. It makes arrays even more costly to copy around everywhere. That's why we have to implement some kind of optimization for passing arrays around to functions and out of functions. For that, we allocate arrays on a heap, yeah, and use pointers or references kind of invisible in the language, and implement copy on write for these references. Thus, arrays are represented like this in the memory, so they have this reference counter for, again, passing around by reference and implementing copy on write, or actually not copy on write. If we have only one reference, we can implement in place updates in that case. Then, yeah, like number of elements, yeah, the stride. Well, actually, we don't keep the stride. We don't keep the size of the elements. We just pre-multiply the size of the element by the number of elements and keep this value, actual capacity, the size in memory in bytes of this portion of the array, and yeah, store it in the array for future reference. Yeah, again, pretty usual kind of representation of arrays. The major thing is this reference counter here. And again, okay, every array knows its size in terms of number of elements and actual number of bytes it allocates or occupies in the heap. Yeah, whatever kind of example how we would store array of 16-bit integers. Then we have closures, and for closures we implement a very similar strategy as for arrays. We keep pointer to the actual code in a code segment that implements this closure, implements the function. Then we have the pointer to environment. Yeah, that's the array of variables or values that function closes over. And what is B? Yeah, B, they call this value witness of the closure. Actually, what these witnesses are basically vtable, virtual table. It's a virtual table with two methods, one for allocation and another for deallocation, or the first one for copying and the other one for deallocation. So every closure knows how to allocate itself. We need that because this environment can have different size. Different closures capture kind of different number of variables from the environment. So we need to know how many of them to deallocate. Yeah, here I kind of disagree with the authors. They say that they do defunctionalization transformation of the program. Actually, they don't. Again, defunctionalization is a transformation, is a whole program transformation. And it replaces kind of function pointers with just indexes. Yeah, that's why we need the whole program. We kind of essentially what defunctionalization does is we collect all the functions that are used in the program, or all the functions we take pointers to, we stick them into a single table of all the functions and use indexes into this table, like their order in the table, instead of pointers to actual functions. In a nutshell, that's what defunctionalization does. And they don't do defunctionalization, they instead do another optimization that's called closure conversion and lambda lifting, or even lambda lifting. And that's the, again, obvious optimization or implementation strategy where we take this function that have some parameters and also captures some values in their environment and replace it with function that have longer list of parameters, which includes everything it captures and the parameters it receives as a function. And then when we call this function, we first give it all these values as arguments from its environment, and then the arguments that caller explicitly passes to this function. That's, yeah, lambda lifting basically, and together with closure conversion. So they do this.
That would be great to creation index.
Ha ha ha. Well, yeah, then I guess we only have time to go over these existential containers that authors employ to implement these any types. Again, any type, obviously, it's a box, meaning essentially a pointer to something we allocate in a heap. So we kind of hide the actual object behind the pointer. That's why we can.
I think it's just clear. Like basically, they box and they do the same things that Python does for small objects. So
Yeah, I don't know exactly what Python does for small object, but yeah, they suggest using the small object optimization. So we use fat pointers or something, where we pass these small enough objects we store in our very fat pointer in place and don't use pointer to the heap at all. But if object is big enough, too big to fit into our fat pointer, we use actual pointer to the heap.
Yeah.
And we have then some unused space in the fat pointer. Yeah, that's like that. And also, again, these boxes use these witness objects. Basically, again, the same virtual table, vtable, which stores the functions that can deallocate, or the function that can deallocate this object. that knows the object layout and knows how to deallocate this object when it goes out of scope, when we need to deallocate it. Yeah, so here we talk about this value witness, which is essentially a vtable to the delete or free method and a copy. Yeah, function to copy and function to deallocate these values. Also, as long as we have this value semantics everywhere, we can easily synthesize equality, that's kind of value equality that compares everything by value kind of recursively, yeah, just as it is, as it works in functional languages and for value types in all other languages. Then, yeah, in-out arguments are essentially pointers, and we implement that using kind of, again, native LLVM mechanisms for passing stuff around by reference. After that, we only have discussion of optimizations and then benchmarks. All right. Okay, let's talk about benchmarks a little bit. They use two kinds of benchmarks. Totally synthetic benchmarks, just programs, kind of stupid programs that don't do anything useful. They generate these programs in large amounts. Basically, they only kind of pass values around, copy them around, or pass as in-out arguments. And they generate these programs in a way so that the programs preserve value semantics. As I mentioned, they benchmark several compilers, several different languages, namely Swift, Scala, and C++, Scala native particular. And because these languages do not natively implement kind of built-in value semantics, mutable value semantics, they have to generate the programs in these languages in a way that they preserve mutable value semantics, meaning they place or they insert more copy around than these languages would perform natively, right? This leads to one particular interesting effect. In these synthetic benchmarks, C++ performs the worst. That's exactly because they use C++ to implement baseline, most stupid, most naive and straightforward this value semantics with copying everything everywhere, like all the time. So when we have only reads and copies and don't use in-out parameters at all, C++ spends a lot of time copying stuff around, even though they compile it with all the optimizations on, like they use 03 optimization level for C++. Still, compiler for sure cannot remove all the copies, all the copying, because yeah, that would contradict usual C++ semantics. Though when we use a lot of in-out parameters and we basically only mutate everything in place, then sure, yeah, in C++ it's business as usual and it performs excellent like it normally does. Yeah, that's kind of not the case for other languages. I don't know why this race, but basically for Swiftlet the performance is constant whether we use many mutations or we use values all the time. The performance is about the same, yeah, on the same level, because yeah, we use this mutable value semantics and they use kind of certain level of optimizations, copy on write mainly, so that eliminates unnecessary copying of the values that never mutates, contrary to again Scala native and C++. That gives this better performance. Swift itself largely, again, implements the same strategy, lots of copy on write. That's why it avoids lots of copying while preserving mutable value semantics when we have no mutations. When we have in-place mutations, again, pretty much all these languages work with the same performance because that's just explicit in-place mutation.
That's right.
I don't know. That's it. Basically, what we have in conclusion, in the end, I think to me the major contribution of this paper is exactly formalizing this mutable value semantics and these second-class references, like really putting this totally formal ground under this stuff that languages were already doing in implementation. Now we understand, okay, how it should behave, what properties it have, what safety guarantees it provides, what we need to do, what analysis or what restrictions we have to put on in-out parameters to prevent violations to value semantics. And thus, it shows where we can cut corners, what optimizations we can implement specific to this mutable value semantics, knowing, okay, that it implements value semantics. So when there is no mutation, we don't need to copy anything. When there is only one reference, we can mutate in place. Unobservable mutations we can just remove altogether. That's another form of dead code elimination when we know that, okay, otherwise it would be copied and would be invisible. And then, they provide this proof of concept implementation that show that, with these optimizations, it really performs in a reasonable way, provides pretty reasonable performance, and there is even some room for more optimizations, merging this approach with other approaches like Perseus that's employed in Coca and Lean 4 languages. Again, further optimizations, remove of unnecessary reference counting access. In certain way, in certain situations, we can skip bumping up and then bumping down reference counters, and that will provide another bits of performance, another bits of speed. Overall, that's solid, and how to put it? Overall, I consider this a solid and promising approach, very suitable for applied programming, so to say.
And you mentioned there are a few languages based on this approach already.
Well, I put the links in the announcement of the event. I can't recall them. Well, one of the languages is Whale, if I remember correctly.
I think it was Whale, Hare, or something like that.
Yeah, another one, changed the name recently, Hare or something like that. That one is explicitly based on this mutable value semantics. At least nowadays they explicitly reference this paper and say that, okay, we implement exactly these semantics in our language. There are several these newer languages that play or implement these second class references, mostly in the form of in-out parameters of one sort of another, and they forbid using these references uncontrollably in structures and places like that, so not passing them around explicitly. But I guess most of that languages predates this work, so they are not explicitly based on this formalization. And these formalization are kind of retrospective, retroactive, analyzes what this actually means kind of after the fact.
All right. So thank you for that.
Yeah, my pleasure. I hope this was kind of informative and understandable. Yeah.